as I was saying earlier, I didn't quite get the book slides figured out, and was uncharacteristically last minute on making my slides, so I didn't have time to figure that out. So I made them with my own Quarto theme. But I'll figure that out, and tonight or tomorrow I'll make a pull request to the repo with our slide decks on it. So hi everybody, I'm Malcolm. So I am going to be covering the ownership chapter of the Rust book, which is one that I picked very intentionally because it was a subject that I wanted to understand better, and there's no better way to have to understand something than to present on it. Um, so this was something that I really, yeah, I've always struggled a little bit with memory management models in general, and Rust takes such a particular opinionated approach to it. You know, it's taken me a little bit of time to digest it, as powerful as it is. So we're going to be talking about Rust's memory management system, basically its ownership system, and a little bit with working with what people call the borrow checker, which is making sure that what you're working with, you know, any variable that's working with data actually is able to do what you want it to do with it without creating an undefined behavior that would be dangerous, that would violate the safety part of what Rust brings us. And we'll also talk about using it in different ways and kind of picking the right ownership model at the right time. You know, do we need to just get the contents of the data? Do we need to manipulate the data, and so on? So ownership is like really important in Rust. It's like built to the core of Rust, and it's something that people both like, you know, love and love to hate about Rust. And so this is one of the things that I don't know if there's any other language where you would have an experience like this, where you write this very simple program, where here we're saying let x be a string hello, and x2 equals x, and then for line 3 we are using x. Like I think in any other language this would run. I don't know any other language that does what Rust is going to do with this, which is to tell us that we can't do that. So it's telling us that a move occurs because x has type string, doesn't have the copy trait. The value was moved here, but then we try and borrow the value here. So it's saying that when we're using x, we define it as this thing in memory, string from hello, and that's what x is pointing to right now. But then we're saying, okay, x, you can just hand that over to x2. But then when we try and use x again, it says that we just can't do that. It doesn't own that value anymore. It got moved somewhere else. And this also happens with functions. So I wrote one that doesn't do anything. That's called take ownership. And when we have another scope like this, we end up taking ownership by virtue of the fact that we're passing it to the parameter that we're using. So if I run this version, I'm going to get basically the same message, that this parameter is taking ownership of this value x. So right now underscore name owns the value of this string hello, because it gets passed along from x to this new value underscore name. So it can happen both within the main scope and in functions outside of that. So one of the messages that it keeps telling me, if you noticed, was that one thing that I could do is clone x, and this works. This will compile. I won't run this one, but this will compile. But what this does is actually make a copy of the data. And by the way, I meant to mention this at the beginning. I mentioned in the Slack that For those of you who are also using the Brown edition of the book that has the interactive quizzes, this chapter was very different compared to the base book. Considerably more advanced, I would say. More complicated, more detailed, very, very interesting read, but more advanced for sure. So I'm only going to cover the content that's in the original book. But one thing that I particularly liked about the Brown edition was the diagrams, the memory diagrams. And so I'm going to use the diagrams from that version of the book, but I'm not going to talk about most of the things that are new in that chapter. But anyway, so when we use clone, in this example, we've got a string that says Ferris, and when we clone it, it actually makes another copy of Ferris. And so it's not really a problem to deal with ownership here, because even though first clone still gets moved into add suffix in this case, or in my example, into take ownership, this value still gets moved into name. It's a different value, and so it's not a problem. It's literally a different object in memory. Okay, so one thing that was here that I think is very helpful about their diagrams is they show what is on the stack and what is on the heap. And one of the things that's quirky about Rust is that values on the stack don't actually have this problem, because it's so efficient to access them and copy them that it's mostly not a big deal. And so so this code compiles. It's probably going to complain about me not using this, but other than that, I get 1 and 1, right? So is that it doesn't bother it at all, because it's implicitly making a copy of X twice. And that's no big deal, because X is very small in this case. It's got a fixed size in memory, and it knows where it is on the stack. And so it doesn't have to go searching around the heap to figure out where it's at. Ooh, this image didn't show up for some reason. So I'll just talk about this in this case. So it's just searching here, and so the stack, stack comes from the idea that they're literally stacking objects on top of each other, and they pop them off. And so it's very easy to find where that is. And so 1 here is on the stack. They know where to find it, and it's easy to copy because of that. It's not very expensive. So the heap is where the major difference between the stack and the heap, besides the efficiency part of it, is the heap is where Rust and other programming languages put things that have a potentially dynamic size. So we don't necessarily know what the size of it is, and so text is a good example of this. We can have text that is of a fixed size and gets included in the binary, but talk about that later. So the string type in Rust, it creates 2 values. It creates a pointer that is on the stack, and the actual value of the data that's on the heap. And so in this case, they're creating first, which is Ferris, and so that's on the stack. The value of first is on the stack, but the value of first is not Ferris. It's a pointer, and that pointer is telling Rust where is this on the heap. And so so this is on the heap, and I liked this example from theirs because it shows what's happening when things get when ownership gets moved around. So in add suffix on L4 here, first is being moved into add suffix. And so if we go down, name takes ownership of Ferris. And so that's what L2 is here. First is grayed out, and name is now pointing at Ferris. So first is grayed out. It's technically there. It's still pointing at it, but it doesn't have ownership. And eventually we'll see that it's okay if this goes away, because Rust is not going to do anything with this anymore. So then in L3, we've done push string. And so this is actually changing the value of the object that it's pointing to. So Ferris has to get changed into a different object. It has to be reallocated in memory to Ferris Jr. So this is a new location in memory, and only name is pointing there. So now first isn't pointing anywhere, but it's no big deal because it doesn't own anything. And so in Rust, what will happen is once it goes out of scope, which is the end of main, once it goes out of scope, it will just be removed, and it's no big deal because it's not pointing to anything. So then we end up going back to L4 here. When we run add suffix, first goes into add suffix, name takes ownership, but then name gets returned, and so it spits back out a value that full takes ownership of. So now full owns Ferris Jr. And name is gone. Name is gone because the scope is over of add suffix. I mostly find that, I think it's primarily our users here, I mostly find that the scope details in Rust are pretty intuitive to our users because the way that scopes, it's maybe a little stricter in Rust, but the way that scopes work in R, I think are at least intuitively similar about what's happening. So anyway, this is gone, just like it would be in R. So in the chapter in the original book, I don't think that they cover box until later, but they do cover it in the new one. This is one of the few things that I wanted to bring up, because this is a way of forcing something onto the heap, even if it would normally go onto the stack. So I have take ownership again, but my type now is box I32, and I'm using box new around 1 to create X. So let me move these over, and we'll run it. Okay. So now it's complaining to us, even though we're just dealing with 1, which previously we used without issue because it can copy 1. We've told it actually to put 1 on the heap, and so now it's saying, well, you can't do that. So because X has been taken over by name underscore name, and so you can't use it again. And so this is what happens in when we're dealing with a box. And so this is the type of example where you might want to use it. Their example is that you've got an object that has 1 million elements, and that's when that automatic copy, if the object is actually really big, even if it's a known fixed size and a known location, it can add up. And so sometimes using a box can be more memory efficient because you have more control over when it gets copied. And so what this is doing is it's saying A is actually a pointer on the stack now, and it points to a heap value that if we had just typed this, it would have been on the stack. So we can force it onto the heap, and that's useful, like I said, when we want to have control over when it gets copied, if that copy detail is actually memory inefficient. Okay, that's memory stuff. Have people dealt with memory languages that manage memory before? Because in R, in Python, and a lot of other languages, we have the garbage collector, which does all this stuff for us.
Only
And we
C
don't
and
have to
C++.
think about it.
Yeah.
Yeah, that was my experience before Rust too, C and C++, and so
These
C++
boxes,
isn't as
yeah.
bad. C's pretty gnarly with memory management.
Well, C++
You have to,
does have the smart pointers, and so this idea,
yeah,
if you've done that before, you would have run into these ideas of moving, and although it's even more confusing in some ways in C++ because you have to take care of it yourself, and sometimes you have to put like a standard move typecast in, you don't know why, and that kind of thing.
yeah, yeah. A lot of these ideas come from C++. I heard once that that Rust was started as like a list at Mozilla, a list of recommendations for working with C++, and they eventually
Oh,
were like, well, let's just like make this official.
Cool.
Yeah. So anyway, we don't, in a lot of higher level languages and even some other compiled languages, we don't have to deal with this because of the garbage collector. In R in particular, you almost never need to even touch the garbage collector. You can just let it do its thing on its own. Um, the downside of that is that the garbage collector has to be running all the time and monitoring the situation and taking care of things. And so this can be much faster, and it can even be faster than C and C++ because of the fact that it has so many guarantees about the memory safety. Okay, so that's ownership. So that's when you when a variable owns something in memory. Um, so working around that, you could do it. You could pass values back and forth. You could pass ownership back and forth. But most of the time when you're working in Rust, what you end up doing is using references, and the majority of the time you're using immutable references because often you don't actually need to change something. You just need to be able to read it. And if you do need to be able to change it, we'll talk about that in a second. This is now we're gonna take X and we're going to borrow it instead of take ownership of it. We're going to borrow it, and so I've changed the function signature to have this ampersand, and then I put an ampersand for X as well. So let me put that in. It's not complaining at me, so that's good. So it's hello. It has no problem with this. So this function borrow, it just borrows name. It doesn't take ownership of it, and print ln has no trouble then using this value. So that's an immutable reference. We can't change it. And coincidentally, when I was preparing my slides or preparing the outline the other day, I was at the library with my daughter. My daughter loves Daniel Tiger, and she wanted to check out this book, Daniel Learns to Share. And so this is in this book. There's a character, Prince Wednesday, this one, who does not have a car when all of his friends have cars to play with. It actually got me thinking about how good this metaphor of ownership and borrowing is for thinking about managing objects. So this is another character called Miscellaneous. She says, you can use my car, you can take a turn, and then I will get it back. Right? So you can borrow it, Prince Wednesday, but ownership of the car stays with Miscellaneous. So it's got to go back to Miscellaneous at some point. He can't do whatever he wants to the car. It's hers. Let's see. What did I want to do here? I don't remember what my point on this slide was. Oh yes, it's that we can have more than one reference here. So I'm creating two references here. I have ampersand X, so that's creating a reference to X, and I'm assigning that to X2. So this now references this value. And then I'm also borrowing X with a reference to X. So I now have two references in play. And so this is also no problem as long as they are. I think this is the same. Mostly it's the same. Yeah. This is no problem as long as the references that we have are immutable references. So X2 can't change this and borrow can't change this. So ownership it stays with X, but it lets X2 and borrow it with the condition that they don't change it. Because if more than one object has it, you can end up with things like race conditions, or you're expecting the data structure to be one thing, and it turns out that it got changed in another place, and it's something else now. Yeah, Jackson.
So I'm just noticing in the kind of grayed out auto-completed types that you have showing that
Yeah,
and string is its own type, I guess. So the reference to the
Mm,
string
hmm.
is itself a type that you then specify in the borrow function. So
Yeah,
you define the type as a reference to, like, it's a reference to a type, and then that's sort of the
yeah.
type definition. That's kind of interesting. So then I guess anytime you might want to call a function against a referenced variable, then it has to be that the reference of whatever that type is in
It
the function
has to
body.
be. Yeah,
Yeah, cool.
if I try and pass it not a reference or vice versa,
Yeah.
then it'll be a problem. Yeah, you're exactly right. It's its own type. And this is like what I think it was Ron that was talking earlier. In C and C++, I'm always kind of like, do I need a reference here? Do I not need a reference here? Like I'm never quite clear. But because of Rust's ownership system, I actually, if I want to do this without, I just want to borrow this without then like passing ownership back, I have to do this. It won't let me do it without it. Whereas in C and C++, you can, kind of do whatever you want and get yourself in trouble. So, so it makes it, that's something that ended up making much more sense to me, is that it's really is its own type in Rust. Okay, so this is Daniel Tiger and O the Owl. This is O's car. Daniel has lent his car to Prince Wednesday in this moment, but O the Owl decides that he's gonna share with Daniel, and here they can both use it because they're kind of agreeing that they're not gonna like go in different directions from each other. They have certain conditions that they expect of each other to play with this, and so this is basically how immutability works. More than one person can use this car under certain conditions, right? So if Daniel starts taking the wheels off and stuff like that, then that kind of violates the conditions, and O is going to be like, wait, this is not sharing. So a lot of the times, though, we actually do want to change something, and Rust makes it really easy with mutable references. So everything is immutable by default in Rust. So firstly, we need to tell Rust that we want to be able to change X in general. Otherwise, we would have a problem with that. But also, we need to add that same mutability bit to the type for borrow and when we create the reference. So here I have these kind of out of order here because this has to go outside of main. But here the function signature, now it says this has to be a mutable reference. And when I create the reference to X, I have to use ampersand mutability, ampersand mut, however you want to pronounce it. The problem is that I've also tried to create a non-mutable reference to X with X2. So let me piece this together. And I did need to actually change this because this is also its own type. It's a mutable reference as opposed to an immutable reference. Okay, so it's complaining to me about this, the fact that I'm, oh, I must have done something not tricky here.
I think borrow
I
has
think
to
I
come
need to,
before the next let.
I need to do something else. Let's try this. Otherwise, I'll try and move it. Yeah, okay. I think that what you said would have worked too. So I do an immutable borrow here, but then I do a mutable borrow here, but then I try and do another immutable borrow down here. And Rust is mad at me about that because it's saying that, well, you can't do that because you've got, something might happen in borrow that changes it. And so that could be undefined behavior. And so when you have a mutable reference, you can only have one at a time. The tricky thing about Rust is that it also is like, it's sort of like, I don't know, a pro and a con that it has so much syntactic sugar on it. Because here it's like, I'm actually doing the same thing, but Rust is smart enough to know that I'm actually not using this. And so it's like, well, you can't have caused a problem with that. So sometimes Rust is so smart that it can hide those things, and I occasionally get myself tripped up on that. So
By the way, did you
with
notice?
yeah.
Sorry, I hate to interrupt, but did you notice that when you are looking at it in the compiler, in the little hinting, it put like when you called borrow, it's you in gray, it says underscore name colon as a hint to like what parameter that's going to be, I guess, on line 4.
Oh, this.
I mean,
Yeah,
that's not
right.
proper. You can't actually type that in. That's not proper Rust syntax. We've talked about this before, like the whole problem with name parameters versus non-name parameters. Um,
Yeah.
it's
No, it's
interesting
just
because
telling you what it is.
just for fun, I tried type that in. It said, "Oh no, it has some error about some kind of structure or something else." It thinks I'm trying to do there,
Yeah.
but
That's an interesting point, because if you type this in, it would
yeah,
be,
it's
oh, I can
fine.
double click
Yeah,
to insert. I can actually say these. That's interesting. But it won't do that for me here.
because
Yeah, because I can be explicit about that here, but this is not valid, as you say.
I just thought
That's
that was kind of
interesting.
weird. But and also it's kind of helpful that
Yeah.
it does point out like, oh, this is the we talked about like how we don't have name parameters, but this will help. This a little hint to help you know which parameter this is
Yeah.
actually going to go into.
Yeah, for sure.
Might help if you have a lot of
For
them.
sure.
Anyway, sorry, I just
Yeah,
thought
I
I'd
like
point
that
that out. It's kind
feature.
of interesting.
Yeah, this is from one of the extensions. I can't remember which one, because
Rust
there are
analyzer.
several. I think it's Rust Analyzer that does this one.
Yeah.
Yeah. Yeah.
Anyway,
Uh,
sorry. Carry on.
no, no, that's an interesting point to bring up, especially since what it brought up here was valid syntax. It just didn't need to be there explicitly. Okay, so when Miss Elena earlier lent her truck to Prince Wednesday and said, "Well, I'm going to lend this to you, but you have to give it back to me later." This was a mutable borrow, because now Miss Elena can't use it, so she decided she's going to use a pretend car instead, because she can't use this one too, because Prince Wednesday is using it right now. So this is apparently a mutable borrow. All right. So that's references and a brief introduction to Daniel Tiger, which I know way more about now than I ever thought that I would. The other topic in this chapter is the slice type. And the example that we spend most of our time with in this chapter is of a string slice. So this is from the Brown chapter version of the chapter. So when we have S and we take a range within S, so the first 5 characters in this case, which is hello, that is a reference to S. And so this is a particular type of value called a string slice, and it has this signature of ampersand str. And this is something that I find I have to think through a lot in Rust, because this is somewhat unique, that it's set up like this. And the other thing is that often, as we'll see, often they're interchangeable, but as long as you're using references, but sometimes they're not. So what this is saying is that I'm taking it for hello and for world, these 2 objects. I am taking a reference to hello and to world on the heap. So it's just this range. But this also, in addition to being able to subset the word here, this also gives us the same memory guarantees that we get with references in other ways in Rust. And so now that I have these values that are referencing these data on the heap, Rust is going to make sure that I'm using it correctly throughout my code, so that I'm not doing any sort of undefined behavior. And it's also in the last one, S2, it's taking a reference to the whole string. And so in this case, S2 is actually just pointing to the pointer S, which is then pointing to hello world. But hello is pointing to the hello component of hello world, and world is pointing to the world component. So they're all pointers, but they're all pointing at different things in and around the heap. So this is the tricky thing, is that the the string slice and a reference string are actually different types, but they're often interchangeably used. So to add more complications to it is that we don't always need to do string from. We can use a string literal, and these are slices. So the type of this value is ampersand str. So the reason for that is that it's not mutable. It is on the stack, I think. No, it's not on the stack, but it is built into the binary when it
Yeah, it's in the
renders because
code.
it
It's
knows
actually in
exactly what it is.
yeah,
Yeah.
it's in the code section, I guess, of memory. So it's just right there in the text of the code.
Yeah.
Text meaning the assembly, the binary text, that is.
Yes, right. Yeah, it's directly written into that. So it can be memory efficient, but so it's not a string. It's a string literal, and they are slices. So it just could be confusing about just the different viewpoints of these values. But let me put this code over because I want to make my next point. Hang on a second, my robot vacuum is starting. Yeah, sorry. I forgot that I had it set to start. Okay, so I think I ran this already. Yes, I ran this already. So this is it's telling us right now, right now it's of this type ampersand str. So it's a string literal is a string slice. And in the function signature here, I have that type. So this is nothing weird. But I wanted to explicitly bring that up because if we use a reference to a string, we can also use this exact same signature. So if I replace hello with these values, this will still compile and work just fine because a reference to a string, you can think of it as a slice of the entire string. And so it's not literally the same type of object, but Rust is smart enough to be like, well, if we just treat it like a slice of the whole value, then we can use them interchangeably. And evidently, this is a bit more idiomatic Rust code to write it like this. When you're working with references to strings, people will, rather than writing ampersand string, they'll write ampersand str because it's more flexible in that respect. And I think that was my last slide. Yeah. Oh, the one thing that I didn't have a slide on that I meant to put in retrospect was that there is mostly when you see people talking about slices, you hear them talking about string slices, but the slices can be of any type as well. So if we had an array of I32s, we can take a slice of that as well. And it's the exact same idea. We're taking a reference to it. Okay.
I have a question, if we're at that part yet.
Yeah.
Is there a good mental model for why a string literal is automatically defined as a reference to a string slice, but the string from is its own separate type? I remember reading that in the chapter, and I couldn't wrap my head around why exactly that distinction is made.
Yeah. It's a fixed size thing.
Okay.
It's where the string from is meant to be a more flexible object. That's my understanding of it anyway.
Okay, got it.
Right.
Okay.
So in the code that says string from, and then you have that literal string. That literal string there is actually also a string slice. It's in the code. Just you don't actually do anything with it because you're only referencing that one time. And then it uses that and then moves it to the heap, right? Dynamically, and then gives you the heap allocated object back from that. which now you can modify since it's on a heap. So you can like append to it, you can combine it with other strings, etc., but you couldn't do it the literal.
Right.
Does that make
Okay.
any sense? I don't know
That
if
does kind of make sense. Yeah.
Yeah. Yeah, and this is another reason why it's a little like counterintuitive to me thinking about it, is like we also have this idea of immutability and non-immutability, and it's like, well, like the string itself is immutable until I add the mutability feature to it. So it's like not a perfect split
Right.
either.
Right.
Hmm.
Yeah.
That's
But
true. You could